Hey everyone, and welcome to The Explainer. Today, we are tearing down one of the most powerful and, let's be honest, hyped up technologies out there, the neural network. We're going to go way beyond the buzzwords, pop the hood, and really piece together how these things actually work. I mean, from a single simple bit of math all the way to a full-blown learning machine. So here's our game plan. We're going to start with the big idea, this concept of a mathematical brain. Then we'll build a single neuron from scratch, see how it makes a decision, and then scale that up into layers. After that, we'll get into why deep learning is so powerful and wrap it all up with the magic trick, how the network actually learns from data.
Okay, so you always hear that neural networks are modeled after the human brain, right? And, that's a great starting point, a great inspiration. But the modern reality, it's way less about biology and way more about just brutally effective, adaptive mathematics.
This quote from Simon Haken just absolutely nails it. See, the goal isn't to build a perfect one-to-one replica of a human brain. Not at all. It's to build a machine that mimics the way the brain performs a specific task. At its heart, a neural network is just an incredibly flexible machine for learning how to map inputs to outputs. Think about it. Mapping the pixels of an image to the label cat, or mapping an audio wave to a sentence. That's the job.
All right, so to understand this massive, complex network, we have to start with its smallest possible component, its fundamental atom, if you will. And that is the perceptron, which was first thought up by Frank Rosenblatt way back in 1958.
The perceptron is basically a single, super simple neuron. It's designed to do just one job: classify patterns that can be separated by a straight line. You can think of it like a simple gatekeeper, deciding if an email is spam or not spam based on some score. It's the little Lego brick we're going to use to build everything else.
So what's inside this little guy? Well, a perceptron has three key ingredients. First, you've got the inputs. This is just your data, whatever it is, pixel values from an image, for example. Second, every single input gets a weight. A weight is just a number that tells the neuron how important that input is. A bigger weight means pay more attention to this. And finally, you have a bias, which is kind of like a thumb on the scale. It just helps nudge the final output one way or the other. And you know what? The math here is surprisingly simple. All the perceptron does is calculate a weighted sum. So let's say we're trying to decide if we should go on a picnic. Our inputs, our x values, could be, is it sunny? Let's say 1 for yes, and is the park crowded? Maybe 0.8 for pretty crowded. Each one gets a weight, w. We really love the sun, so that gets a weight of 5, but we hate crowds, so that weight is -2. You just multiply each input by its weight, add them all up, and then add that bias, b, maybe it's -1, representing our general laziness. The result of all that is our score, v. It's just a simple linear calculation. But here's the catch. That simple weighted sum, it has a big limitation. It can only ever model things that follow a straight line. So what happens when the problem is way more complex than that? Because let's face it, the real world is messy. It's complicated. Data rarely falls into these neat little piles that you can just perfectly separate with a ruler. Think about trying to identify a dog in a photo, or understanding sarcasm in a sentence. Simple linear models, they just completely fall apart. And this right here shows you exactly what I'm talking about. On the one hand, you've got what our perceptron can do so far. It can draw a straight line. But on the other hand is what we needed to do, which is to learn these complex, curvy boundaries that actually fit real-world data. And to get there, we need one more crucial component. And this is it. It's called the activation function. The best way to think about it is as a decision-making switch that we bolt onto the end of our neuron. It takes that weighted sum v we calculated a second ago, and it squishes or transforms it. By applying this nonlinear function, it allows the neuron to decide whether to fire or not, and how strongly. This is what lets the whole network learn those complex, curved patterns we're after. So this right here is the complete formula for a single artificial neuron. You take that weighted sum, that's the w.x plus b part, and you pass the entire thing through our nonlinear activation function, phi. And that gives you the final output, y. This exact calculation is the fundamental operation happening millions, even billions of times inside a big neural network. Okay, so we've built one neuron. That's cool. But one neuron, even a fancy one with an activation function, is still pretty limited. The real power, the real magic, comes when we stop thinking about individual neurons and start organizing them into layers. So here's how we scale this thing up. We basically stack our neurons vertically into a layer. Now here's the critical part. Every single neuron in that layer sees the exact same input data. But, and this is key, each one has its own unique set of weights and its own bias. That means each neuron becomes a specialist, learning to look for a different pattern or feature in the input. And together, as a team, they transform that raw data into a much richer, more abstract, hidden representation. But why stop at just one layer? I mean, the real breakthrough, the thing that puts the deep in deep learning, is what happens when you start stacking these layers one after another, creating a deep neural network. The data basically goes on a journey through the network. First, the input layer just takes in the raw data, the pixels, the sound waves, whatever. It passes that to the first hidden layer, which might learn to spot really simple things like edges or colors. The output of that layer then becomes the input for the next hidden layer, which might combine those edges to find shapes, like an eye or a nose. This goes on, with each layer learning more and more abstract ideas, until the final output layer takes this super rich representation and makes its final call. So why is this stacking so powerful? Well, it all comes down to this kind of mind-bending idea called the universal approximation theorem. And what it basically says is that a neural network with just one hidden layer, if you make it wide enough, can theoretically approximate almost any continuous function you can think of. It's like a mathematical guarantee that these things can learn just about anything. Now, while one giant layer could work, what we found in practice is that using multiple deep layers is way more efficient at learning complex patterns. So, we've built this whole structure, right? But we've kind of skipped over the most important part, the million-dollar question. How in the world does the network figure out the right values for all of those millions of weights and biases? How does it actually learn? The answer is a brilliant algorithm called backpropagation. At a high level, you can just think of it as a clever system for assigning blame. So when the network makes a guess and gets it wrong, backpropagation calculates that error. Then, using a bit of calculus, it works its way backwards through the network, from the final guess all the way to the first input, figuring out exactly how much each individual weight contributed to that mistake. And it tells us which way to adjust it to do better next time. The entire training process is really just this simple loop that goes over and over and over. Step 1, the network takes an input and makes a guess. We call that the forward pass. Step 2, we compare that guess to the correct answer and we calculate how wrong it was. That's the error. Step 3, we use backpropagation to send that error signal all the way back through the network, assigning blame. And finally, step 4, we adjust every single weight and bias just a tiny, tiny bit in the right direction. And then we do it again and again, millions of times. And that's learning. So when you boil it all down, all of this complex stuff we call learning is really just a huge optimization problem. We're just trying to find the one perfect configuration of all those millions of weights. It's like trying to turn millions of tiny dials that makes the network's prediction error as low as possible. It's a slow, gradual process of tiny nudges, all guided by backpropagation, that eventually carves the network into a solution for the problem. And there you have it. That's how you build a neural network. We started with a simple weighted sum, we added a nonlinear switch, we stacked them up into deep layers, and then we gave the whole thing a way to learn from its mistakes. And from these surprisingly simple mathematical building blocks, we've created a tool that is solving some of the most complex problems we have in science and technology today. It really makes you wonder, doesn't it? What's next?